Welcome everyone to this edition of the New Technologies in Mathematics seminar. And today we're very happy to have Elli from Imperial College London. And she will tell us about machine learning, the G2 symmetry. Thank you to her.
Thank you so much. Okay, first off, thanks to the organisers for giving me the invitation to come and give the talk. Yeah, it's my first time in Harvard, so it's nice and exciting for me to be here. And yeah, I guess for anyone who I haven't already spoken to, I'm currently a Schmidt Sciences Fellow at Imperial X. And roughly speaking, my research is using AI or machine learning techniques to study properties of geometry. I personally have a string theory background, so I mostly study Calabi-Yau and G2 geometry. And today's talk is going to be focusing on G2. So in the first half of the talk, I will be discussing the results of this first paper, where we used a neural network to predict some topological properties of G2 manifolds. And then in the second half of the talk, I will be discussing some work that I'm currently working on with Magdalena, and this is trying to numerically approximate G2 holonomy manifolds. But this is sort of like a work in progress. So, firstly, an overview. So I'll start off by just motivating why we should be using AI and machine learning techniques within pure math. And I'll give you some examples of this from the literature over recent years. And then I'll give you just some basic definitions in G2 geometry, namely G2 structures and their torsion. And then I want to introduce to you a special kind of G2 manifold, which are these Calabi-Yau links, as these were the ones that we looked at in our first paper. And then I will move on to the results and show you how well our neural network did at predicting certain topological invariants of these Calabi-Yau links. And then in the second half of the talk, as I said, I want to discuss kind of a rough framework, which I think can be used to try to use neural networks to numerically approximate G2 holonomy metrics, using already what's been done for approximating Calabi-Yau metrics. And then finally, I'll conclude the results and give some comments on my hopes for the future.
You can share the full screen. It's like the small screen.
Okay, perfect. I should say, yeah, of course, please do stop me at any point to ask questions. So yeah, to start off, as a motivational speech of why we should be using AI in pure math. So pure math is obviously about finding patterns, coming up with conjectures, and then proving these statements. And machine learning is obviously very good at picking up patterns within data. So it makes sense for us to use these techniques to look for patterns within mathematical data, help us formulate the conjectures. There's also a lot of work being done at the moment on formulating proofs of mathematical statements. So this is also a very interesting area of research. And then also there's been a couple of examples of using machine learning to look for counterexamples to conjectures. So as well as proving conjectures, we can also use machine learning to disprove conjectures as well. And it can also be used to speed up difficult computations by manipulating, using symbolic AI or manipulating expressions. And then finally, as we'll see in this talk, it can also be used to approximate solutions to PDEs, which there's no known exact solution. So just a couple of examples from the literature. There's this first paper, which you may have heard of, which is a collaboration between researchers at Sydney, Oxford, and DeepMind, where they used gradient saliency analysis to discover a new relationship between the algebraic properties and the geometric properties of knots. And then on sort of the more formal math reasoning side, there is alpha proof, which is an AGI system for formal math reasoning. And it couples together a pre-trained large language model together with a reinforcement learning trained to prove mathematical statements. So yeah, this is a math seminar series and not a string theory seminar series. So I thought I'd at least just include one slide in this talk introducing the idea of string theory for those who may not be familiar. So string theory is a theory of quantum gravity, where the main premise of the theory is that rather than everything being made up of lots of zero-dimensional point particles, instead everything's made up of a one-dimensional string. And then you get the different particle properties that we see from experiments as different vibrational modes of this string. And then there are several different versions of string theory. They differ in the kind of strings that they allow and the types of symmetries that they have. And M theory is another theory which connects all of these different versions of string theory together via various different dualities. So one of the important points of string and M theory is that both theories require there to be extra spatial dimensions. So, of course, we're used to experiencing one dimension of time and 3 dimensions of space. But in string theory, we have 10-dimensional space-time, where we have 9 dimensions of space, and M theory is an 11-dimensional space-time, where we have 7 dimensions. 10 dimensions of space. So one way that string theorists get around the problem of why we haven't experienced these extra spatial dimensions is to say that they exist on some small compact manifold, and it's too small to be detected by experiments. So in this case, your 10 or 11-dimensional space-time is split up into the usual 4-dimensional Minkowski space, and then some small compact internal geometry, which here is labeled X. And the geometry of space-time and the physics of the theory are intimately linked. So the shape of your space-time, and in particular the shape of the internal space, influences things like what type of particles can exist, the strengths of forces, the types of symmetries that you have, etc., etc. And we would like to impose some conditions within string theory. Firstly, we would like to be consistent with general relativity. So we'd like our space-time to satisfy vacuum-Einstein equation. And also we'd like to have some supersymmetry. Supersymmetry is the symmetry between 2 types of particles, bosons and fermions. So minimal supersymmetry says that every particle in the standard model has a supersymmetric partner particle, which differs by spin half. So a boson has a supersymmetric fermion partner and vice versa. You can have extended supersymmetry where you have basically more supersymmetry generators, and therefore you have more complex relationships between the particles, and you have more new particles. But we haven't detected any supersymmetric particles experimentally, so ideally we'd like to have minimal supersymmetry because, well, we like to have supersymmetry because it solves some problems, to say it quickly, shortly. But we don't want to have too much supersymmetry that we have all these extra particles that we haven't observed experimentally. So the 2 conditions of having a minimal amount of supersymmetry, which solves the problems that we like, and also ensuring that we satisfy the vacuum-Einstein equations, impose some constraints on the internal space. And in string theory, this means that the internal space is a Calabi-Yau threefold. And in M theory, this means the internal space is a compact G2 holonomy manifold. So this is why I came to study G2 geometry, and this is why string theorists are particularly interested in these types of manifolds. So now over the next couple of slides, I just want to show you a couple of examples of the different ways that machine learning is being applied to geometry. So the first example that I'm aware of, at least, of applying machine learning to geometry was from 2017, and it was using supervised learning to predict topological features of Calabi-Yau manifolds. And then since this initial work in 2017, there's been lots of work in this type of problem. This is just a couple of examples, but there are many more. And yeah, these kind of experiments are predicting all kinds of geometric properties of different types of geometries. So this is nice because often we know the formula for which to compute some property of a geometry, but sometimes this formula can be difficult and computation intensive. So if we can train some neural network or some supervised learning to predict this feature with a very high degree of accuracy, this can potentially help us to speed up these computations. But arguably a more interesting application, I think, is using things like unsupervised learning or feature extraction methods to learn new geometric features. So this is, this could be, you could use sort of a clustering algorithm to sort of cluster equivalent geometries, and then with the learned embedding, you could then try to discern features of why the algorithm has decided one geometry is equivalent to some other geometry. And then there's also things like this knot theory paper where they used gradient saliency analysis. So you could train some supervised learning algorithm to predict some property, and then look at the gradients of this learned function with respect to different features and discern what type of features are important in predicting some output. And this can therefore lead to coming up with new relationships between features. So another potential application of applying machine learning to geometry is approximating metrics. So one of the big problems that we have in string theory is that there is no method for getting the exact Ricci-flat Calabi-Yau metric or the G2 holonomy metric. And we need the metric in order to compute details of the theory, like the masses of particles and the coupling constants, etc. There's some properties of the theory that you can obtain just from knowing the topology of the internal space, but really in order to know the full details of your theory, you need to know the exact metric on the internal space. So in the Calabi-Yau case, there are some numerical methods for approximating the metric, but these can be very slow or computation intensive. So in the last 5 years or so, there's been a lot of work being done on using neural networks to approximate these metrics, including this work by Mike and Elli. So my question is, can we use what's being done already for learning Ricci-flat metrics on the Calabi-Yau manifold and trying to use this to learn Ricci-flat metrics on G2 holonomy manifolds? And there's been no explicit work of this yet. I think this is because, of course, constructing G2 holonomy manifolds is, of course, much more difficult than constructing Calabi-Yau manifolds, because to determine, well, to prove that your manifold is Calabi-Yau, you just need to, compute the first Chern class, and if it's 0, then it's Calabi-Yau. Or to prove that a manifold is G2 holonomy, you actually explicitly need to compute the metric and then check that it's invariant under G2. So this is sort of additional motivation as why learning G2 holonomy metrics would be particularly interesting. This one?
Yeah. Just so that it doesn't like overlap with all of that. Yeah.
Okay, so we've seen how machine learning can be used to learn properties of geometries and also to learn metrics on geometries. It can also be used to generate the geometries itself. And this is something that I've been working on over the last couple of years. So there's a famous construction of Calabi-Yau manifolds. It starts from certain types of polytopes and their triangulations. So in these first two papers, well, in this first paper, we used a genetic algorithm to generate these polytopes. And then in the second paper, we used a reinforcement learning algorithm to generate the triangulations of these polytopes. And there's also this paper by Brooke Cornell, who also use genetic algorithms to generate the triangulations. So what I think is most exciting about this first paper was that we were able to generate Calabi-Yau manifolds that weren't part of any existing data sets. These really were new geometries into the literature. And then in the second paper, the most exciting result, I think, was that we were able to impose additional constraints into the reinforcement learning algorithm And we're able to then generate Calabi-Yau manifolds with a specific property. So this is particularly nice from the string theory point of view, because in theory, you could say, I want X, Y, and Z from my theory. And then by inputting these constraints into your generative AI algorithm, you'd then be able to generate some internal space geometry that satisfies these constraints. So these are just first steps in this direction, but I think this sort of framework has a lot of potential in string theory. All right, so for the rest of the talk, I'm going to be focusing on G2 geometry. So over the next couple of slides, I will introduce some of the basic definitions. So there are equivalent different definitions of G2, but the one I like to use is it's a subgroup of GLR7 that preserves this 3-form 5-0. And a G2 structure on a 7 manifold is just any 3-form that can, such that it can be, at a point on the manifold, it can be defined as the pullback of some frame acting on 5-0. So essentially, it's just the reduction of the structure group of the frame bundle to G2. Then given a G2 structure, we can get an induced metric and volume form using the following identity. And then a G2 manifold is just any 7-dimensional manifold that admits a torsion-free G2 structure, where the torsion of the G2 structure is defined by the Levi-Civita connection coming from the induced metric. And it can be shown that having a torsion-free G2 structure is equivalent to your G2 structure being both closed and co-closed, and also it's equivalent to the holonomy of your induced metric being contained within G2. And an important point to note is that if we want to have full holonomy G2, like in the end theory case, then the fundamental group of our manifold must be finite. Okay, so now I want to introduce to you a specific type of manifold that admits G2 structures, and these are Calabi-Yau links. So in general, a link, so if you have some complex analytic variety with an isolated singularity at the origin, and then you take the intersection of this variety with a small ball centered at the origin, then this is what we define to be the link. And suppose now that our complex analytic variety is defined as the affine hypersurface of some weighted homogeneous polynomial, such that the degree of the polynomial equals the sum of the weights, then this is what we refer to as Calabi-Yau link. This is because using the Hopf vibration, we can describe this Calabi-Yau link as an S1 bundle over some Calabi-Yau orthofold. Now, if we just consider the case where n equals 4, so if we go back, this is now an S1 bundle over some Calabi-Yau threefold within P4. Then in this case, because it's an S1 bundle over Calabi-Yau threefold, the link is 7-dimensional, and it can be, first I should say this is a contact Calabi-Yau manifold, which just means it's a Sacchian manifold that has a transverse Taylor structure, where the Calabi-Yau structure is given in terms of the contact one form. And it can be shown that this 7-dimensional Calabi-Yau link, which is one of these contact Calabi-Yau manifolds, admits a G2 structure given in terms of the contact form. So in a case where the G2 structure is torsion-free, this is a G2 manifold. So these are the kind of geometries that we're going to be looking at. So to generate a data set of Calabi-Yau links, what we did is we took the set of weight vectors describe a weighted projected force space such that the anticanonical hypersurfaces are compact Calabi-Yau threefolds. And this is a data set of 7,555. For each of these weight vectors, we then constructed a Calabi-Yau hypersurface that has the right singularity structure. Because remember, I said slides ago, I want to have an isolated critical point at the origin. So with the weight vector, this essentially defines some basis of monomials, and then I can assign different coefficients to these monomials to define different Calabi-Yau hypersurfaces. We want a Calabi-Yau hypersurface that has this isolated critical point at the origin. So we basically just, we signed every A to be 1, and if that gave us the right singularity structure, we were like, okay, great, save that. Otherwise, we sort of searched different coefficients in order to have this isolated critical point at the origin. And then from each of these Calabi-Yaus, we then constructed our links. So, okay, now we want to look at certain topological properties of these Calabi-Yau links. So, as I said, the link is an S1 bundle over a Calabi-Yau threefold. So one of the properties that you can consider is the set of Hodge numbers of the Calabi-Yau base. And then also said that these Calabi-Yau links are contact Calabi-Yau manifolds. So yeah, which are certain types of Sassakian manifolds. So you can also look at the mixed Hodge numbers of the transverse scalar structure. So these are two topological properties that we looked at. And this is before any kind of machine learning, just by plotting the two different HT1 Hodge numbers against each other, we found this interesting relationship that the Sassakian Hodge number is bounded above by the Calabi-Yau Hodge number. So we put this as a conjecture. I think there probably is sort of a nice, simple way of explaining this, but I'm still yet to figure this one out. So later, if anyone has any ideas, I'd be interested to hear your thoughts.
Spatial sequence.
In the
chronology.
Yeah, that's interesting. I haven't thought about this. Because yeah, both the transverse scalar structure coming from Sassakian and the...
There's a topological statement here.
Yeah. Yeah.
And the way that the spatial sequence starts off with like the odd after the two chronologies, and it's like these kill pairs of things. And so typically you get the vibration has less than or equal to the chronological vibration. So.
Okay, yeah, I don't know much about this, but I'd be interested to hear about it afterwards. I'm not sure why my animations are all. Oh, okay. I'll just have to explain the missing images here. So yeah, we trained a neural network to predict the Sassakian Hodge number given as input the weight vector describing the ambient weighted projected space. And the formula that we use to compute these Sassakian Hodge numbers includes computing the dimension of certain linear subspaces of the Milnor algebra, which is defined from the polynomial itself. But we had a very simple neural network with just very few parameters, and it was able to predict the Sassakian Hodge number, as you can see here, with very high degree accuracy, around 97%. But this was kind of surprising to us because the formula that we used anyway to compute this topological property includes the actual defining polynomial of the Calabi-Yau rather than just the set of weight vectors. But this kind of leads you to believe that there's a simpler formula for computing this Hodge number just in terms of the weights. So one thing we did is we applied a symbolic regression to try and approximate this formula. And we came up with something which also managed to get over 95% accuracy, but we haven't managed to come up with an explicit formula. But we did kind of try different polynomials to see if they have the same Hodge number, and it seems like you just need the weights, like different polynomials coming from the same weighted projector space do give you the same Sasaki Hodge number. So it seems like there is a formula out there to get this invariant in terms of the weights, but we're still looking for that exact formula. Okay, so we've seen that in some cases, properties, geometric properties like topological invariance of the G2 manifolds can be learned with machine learning, but what we really want to know, at least from an M theory point of view, is we want to know the metric. So now in the rest of the talk, what I want to do is describe a potential way to do this. And unfortunately, unlike in the case of Calabi-Yau's, there are very few constructions of compact holonomy, G2 holonomy manifolds. So there are sort of just 3 constructions, but they all follow the same kind of procedure. So the first thing is you construct some simpler pieces, which are either flat or have holonomy SU2 or SU3. And then the next thing you do is you glue these pieces together in some way to create a compact 7-dimensional manifold with a G2 structure which is closed but not co-closed. But D star phi has a small enough norm that you kind of think of it as an approximate solution to the torsion G2 structure. And then in the last step, it was a result by Joyce that if you have a G2 structure that's closed, not co-closed, but has a small enough norm, then you can perturb to find a nearby one that is torsion within the same homology class. So let's just briefly review these construction methods. So the first one by Joyce is you start with T7 and you take the flat metric coming from R7, and then you look for some group of isomorphisms, take the quotient of T7 by these isomorphisms, and now you have a G2 structure where we have some singularities in our G2 manifold, but these are nice enough. Well, if you pick the right isomorphism group, the singularities are nice enough that you can resolve them. The second construction method by Gogolev, which was later developed by Corti, Haskins, Nordstrom, and Virginie, is the twisted connected sum construction. So in this case, you start with 2 Calabi-Yau threefolds that are what's called asymptotically cylindrical. And then at these asymptotic ends, you can then, first off, sorry, actually, you could fiber each of these with an S1 and then glue them together at their asymptotic ends. And then you have a compact G2 manifold. And then finally, it's the Joyce-Karagiannis construction, which is kind of an extension, really, of Joyce's first construction, where now you have a Calabi-Yau threefold with an anti-holomorphic involution. And this involution has a set of fixed points. You then describe a harmonic one form on this set of fixed points. And then by taking the fibering your Calabi-Yau threefold with an S1 and quotienting out by your sort of fixed points, then you have the G2 orthofold, where again, singularity is resolvable. Okay, so now I want to define for you a framework by which we want to learn our torsion-free G2 structure. So I should say that this sort of framework was taken from, I might go back, but it was taken from a paper last year by Georgi, who's actually giving a talk tomorrow, I fear. But essentially, they summarize the task of finding an approximation to some tensor field on a manifold using a neural network by doing the following. First thing you need to do is you reduce the problem of approximating your tensor field to approximating some function, scalar function on the manifold. The next step is you turn the system of PDEs for which your tensor field is a solution into a variational problem. So in this case now, solving the system of PDEs corresponds to minimizing some loss functional over the function class of U. And then the last step is that you represent your scalar function U as a neural network. So this then defines a restricted function class. And then approximating your tensor field just becomes the process of training your neural network to minimize the loss function. Okay, so how do we go about doing this for trying to approximate torsion-free G2 structures? So my idea is essentially just to take the existing constructions, so either the twisted connected sum or the Joyce-Karagiannis construction. And first step would be to learn the simpler pieces. So this could involve using the approximations for the Calabi-Yau metric that have already been done using neural networks. So then you get an approximation, your sort of small torsion G2 structure. Then you want to glue these pieces together by whatever method you're looking at. And then the final step, you want to solve some nonlinear elliptic PDE in order to find the perturbation term such that you find your nearby torsion-free G2 structure. So of course we have Yidi and Mike's paper with Daniel from last year. So in this paper, you were using approximations for the Calabi-Yau metric to come up with approximate harmonic one forms. So in this case, essentially, it's doing torsion-free G2 structure. Should I decline this? I'm assuming.
I'm sorry, someone was sharing the screen. Okay.
So let me just explain this in a little bit more detail. So, you know this person? Okay.
I should have broken.
Yeah. Good. Okay, so there's really, going back to this framework, two big challenges are going to be finding some reduction of the problem of learning R3 form to learning some scalar function, and then also coming up with the right variational objective. So I haven't sort of got all the answers here, but one suggestion that I have is that trying to, well, basically define some approximate basis of two forms on the manifold, and then writing our perturbation term or approximation for our perturbation term in terms of some scalar function dot producted with, so basically just taking the linear combination of some linear combination of these basis two forms, and then you just want to find the coefficients of these. But there may exist sort of smarter way of finding a reduction of your problem to looking for scalar function. This is just one idea that I had. And then I don't want to go into too much details about the derivation behind PDE. If you want to look at all the details, it's in Joyce's original paper. But essentially, this is the system of which gives us our nonlinear elliptic PDE, and then we can use this to phrase our problem into a variation objective and then define some loss function over which we want to minimize.
What loss function would you use, or you propose one?
I haven't actually defined a specific loss function yet. I don't know sort of what properties of the loss function are particularly useful. Obviously, in the Calabi-Yau case, you have like the margin pair loss that people tend to use, but you could have.
Yeah, that's right. That's kind of the idea. This is, I mean, of course, you can just take the norm squared. So that's works. This is probably complicated. Very non-linear because it's completely true. But that would be the obvious. Not really anything. Norm from D star fonts.
I think then that you might move outside of your cohomology class of your original.
Well, then you just have, well, your phi is 5 plus d8, so that keeps you in the right. That's why you wrote 5 plus d8.
Oh, you're saying using, sorry, the norm of eta?
Well, I mean, if
I think we have various norms.
I mean, if you're just trying to solve, I mean, you automatically solve the d5 equals it. You're trying to solve d star phi equals norm squared. So it's the obvious loss function. But the only thing about it here, of course, is you have to compute this d5 to do the star, so that makes it.
Yeah, you have to compute, some approximate Hodge star.
At least it exists as a loss function.
Yeah, true. Yeah, you could use your approximation phi to come up with some approximate Hodge star operation, and use just d phi, d star phi. That's probably the simplest thing to try. Whether it's the most efficient loss function, I'm not sure. Yeah, there's a lot of questions for all of these steps, so I haven't fully worked out the details. But then once you have sort of a reduction of the problem to looking for the scalar function, and then you have defined some variation objective, some loss function, then the problem can be stated as learning the torsion-free G2 structure from some initial G2 structure that you have from steps 1 and 2, can be phrased as training your neural network phi to minimize your loss function on in order to search for your perturbation term. Okay, so just some concluding remarks. So we've seen machine learning can be used to predict geometric features, including topological invariants. It can also be used to come up with new features and conjecture new relationships between features. It can also be used to approximate metrics, for which there is no known exact solution, and it can also be used to generate geometries with specific features. So there's been a lot of work since that initial work in 2017 of applying machine learning to Calabi-Yau geometry, but there hasn't yet been a lot of work done for G2. So we have a lot of room for things to be done. In this talk, I showed that we can train the neural network to predict the Sasaki and Hodge numbers of these Calabi-Yau links. And my goal for the future is to use what's been done for learning Ricci-flat Calabi-Yau metrics to try and learn holonomy G2 metrics. So I'm currently working on this in terms of the twisted sum connection, but you can also try and do this for the Joyce-Carabianis construction. Yeah, thank you very much for having me again. I'm happy to take questions.
Thanks. So like in some of these constructions, and in particular, I would think the twisted connected sum need to overlap patches.
Yeah.
Is that how you plan to do it? Like in this dot, I guess do when it constructed the SU3 structure, try overlapping patches.
Yeah, I think we're going to have to, because also the twisted connected sum construction has this these asymptotic ends, so you could sort of our thought is maybe that the metric in one side and the metric is very different to the metric in the other side, and is very different to the metric in sort of this cylindrical region. So I think we're going to have to be
We played a bit with probably trying to just look at metrics on S2 plus S2 and so forth. And we found that this patches were very problematic. We were kind of trying to seemed to me that when there's some preliminary work to be done to make problems with patches work. So just even one should choose something much simpler than G2 and just kind of iron out the prescription to make things work with patches, because it would be nice to do that. But,
I mean, yeah, you could even just start with.
You get. I mean, yeah, I'm not sure it's. I mean, they were able to get result, but I think in general, once, because if you're forced to patches with not exactly, but with a loss in the transition functions, you have to satisfy a loss, which is what they did. Then, by varying, going outside of the space of valid transition functions, you get lots of things that look like solutions, and you can drive down the other losses a lot, at the cost of a little bit of this transition function loss, and so the thing doesn't really work.
Yeah, and it's, I guess, then going to be extra dependent on the points that you sample. And...
Yeah. So it was kind of a mess, and so what that suggested to me is not that it's not worth doing, it's to step back and understand that aspect of the problem before you try using a complicated thing.
Yeah, I'm not. Yeah, for twisted connected sum, it's hard to imagine doing linear global structure straight off.
Yeah, it's very natural to glue two things together. I mean, that's a very useful ability to have. I'm saying that I want to warm up problem.
Yeah, maybe we should start simple. At this stage, we're constructing databases of these to connect some of the tops and things and looking at geometric properties, but we hope at some point to do some metric.
And just the original, page metric on the K3.
Yeah.
So do you have any sort of quantitative estimate of how good is the method in terms of errors, just trying to find, say, the metric or anything that you can put numerical error?
You're coming back to Calabi-Yau, so you understand.
Yeah, I mean, I think with the Calabi-Yau case, you can, measure things by just looking, there's different error measures that people come up with, but things of just how Ricci-flat is the metric approximation that you've come up with. And I guess, we want also Ricci-flat metrics. That's one thing you could look at.
But in terms of performance, say roughly how many digits you think you could get right? Whichever metric.
What accuracy?
Yeah.
Like that.
Roughly. That's sort of ballpark.
What kind of metric are you using?
Any metric.
To Ricci tensor, or this ratio of the two volumes. It's supposed to be 1. Maybe it's 1.01. Let's say the accuracy is 10⁻².
Yeah. I mean, I haven't actually explicitly worked on metric. This is new for me, so I'm not sure exactly what, even in the obviously no one's done it yet, but in the Calabi-Yau case, I'm not sure what kind of measures. I mean, do either of you remember kind of the volume example?
Yeah, I mean, that was what we spent a lot of time in our paper trying to. I mean, our system back in that was 10⁻².
10⁻².
If you have a manifold with a lot of symmetry, like the Fermat, accurate. It means that you have a lot. I mean, it's not that the symmetries directly help you, but it means that when you do your series expansion or your network, you can just do a series expansion for that one. You can eliminate lots and lots of terms because they don't respect the symmetry, and you just get very high order in terms of the series.
And so the volume measure you're saying is about 10⁻²?
For the Calabi-Yau, the simplest one is the ratio of the
approximately.
The bigger neighborhood, bigger neighborhood.
And what kind
it's
of...
interesting to know what's a good measure for G2, but for Calabi-Yau.
Yeah, I mean, also you could look at the Ricci flatness, I guess.
Yeah, that's right. You could do Ricci flatness.
Yeah, what was the sort of results on the Ricci flatness on the Calabi-Yau?
It was similar. It probably wasn't as good because you're taking.
You check the.
Yeah, we probably did. Other papers did Ricci-flat.
So yeah, I'm not sure. I don't think I could put an educated guess on sort of how well I think the G2 or like what kind of measures we would be looking at. But yeah, it's a problem that we definitely need to think about. Get there.
Do you think you could adapt your methods to like spin 7? What were the special ones?
I think as long as you have a system of PDEs in which your metrics is a solution, and you can basically do steps 1 and 2, then I don't see why you can't try it. So yeah, if you can, I mean, there's kind of always ways of doing this for whatever problem you're looking at, but as long as you have some nice variational problem, then I can't see why not.
Maybe another one. It's like, is there any advantage to try to solve the variational form of the PDE, to solving the PDE? From the point of view of like the architecture or the comparisons of the neural network.
What do you mean, just like take this one?
For example, I mean, instead of looking for the variational formulation of this, just take the normal value as your loss function.
Yeah.
It's not a trick question. Like empirical evidence is good for me, but just if you found out something that somehow suggested that the variational formulation could be better for whatever reason.
I'm not sure exactly if it's better. It's just what I've seen people do. I've only ever seen people put it into variational formula, so you have some loss.
Well, there is. I mean, the kind of thing that comes up is if you take like the L2 norm, then you get lots more solutions. So that's if you take the L1 norm, you get this potential kind of non-analytic things happen.
Yeah.
So those are like the problems that you can.
Okay, because you will get trapped in many more local minima and you just try to minimize that or everything all the time.
So trying to just simplify your loss landscape.
Well, it's like because like if you look at like the Einstein equation, so then that one was actually problematic in various ways. I mean, so if you take like the norm squared, the Ricci square, try to minimize that, then the minimum of that can also be things where points, and so things like some derivative of Ricci, some complicated combination of derivatives on Ricci. Those are actually not just Ricci-flat metrics; those are more general things.
Yeah.
So if you can find a function where just the critical points are what you're looking for, then that is better.
Yeah, that makes sense. Yeah, I welcome any. So yeah, this is just my kind of first thoughts on trying to do this, but there's lots of things that need to be ironed out. And yeah, probably.
And what was exactly this hedging functional? Something, some senses.
Yeah, so this is kind of I guess what we were talking about earlier. Like you can look at the G2 flows. It's like
yeah, well, I'm just stepping before we talk about a flow. We can talk about this functional. Right? So there's this mentioned for those, and it was on some sense negotiated like a variation of functional, but it's not such an expert. So I'm not sure you can do that. It's just as complicated. It's a very complicated function that requires computing that's volume for taking 1/3 or something, all sorts of weird stuff. So it is a variation.
Yeah, I think I mean, I sort of was thinking like just using the, you know, the maybe I haven't put it in actually. I know I did. This system PDEs from Joyce, but I think like once you get your like approximate solution, you kind of use anything you like to try and find any other functional. Life left.
You don't have other questions? That goes speaker again.